We'll wait for 5 more minutes and then we will start. Okay? We'll wait for 5 minutes.
So, what are we discussing today?
So hello guys, good evening. So let's start with a very small recap of what is that we are trying to do in week 3. Okay. Now today's discussion is centered around week 3 contents. Okay. So that means that if you have any queries regarding week 1 and week 2, you can ask. Okay. So that's the idea. So now what did we look till week 2 in the sense? So we assume a parametric form for Px. Okay, so the data which is there, now we assume that it is coming from a specific distribution. Now we will call it as P theta. Okay, now then we compute how far is this Px and P theta. Okay, so now then we need theta star such that now whatever P theta you have considered, so it goes as close to Px. Okay, now this is the overall idea. Okay, you are using a distance metric. So now this can be any distance metric. So we are not fixing it to be anything. In a generalized version, we are not fixing it to be anything. So as we go along, we go ahead and fix it up. So now, then how do you actually, what is the distance metric that you will use? For that, we took the help of information theory. So there was one question regarding to one of the code length. So you are using a model Q to encode the data and P generated from P. So Q here is P theta and P that I'm referring to is actually Px. Okay, so then the average code length, no, it is exactly the way in which we have looked at here. Okay, to answer that specific question since it came. So I'm just answering that. So finally, it boils down to, I'll not go into the details of entropy and other things. So it boils down to the KL divergence. Okay. So the distance metric that we shall be using, the distributional divergence metric that we shall be using is KL divergence. Okay. So now finally it boils down to, okay, now this is how you have the KL divergence between PV and P theta. Okay. So now as you expand, now you see this term is independent of theta, it goes off. So this is what you get finally. Okay. Now here the view is you are reducing the divergence. You are reducing the KL divergence. Okay. Now as it turns out, now it is similar to maximizing the likelihood. Okay. Now this log P theta V which is there is known as the likelihood, the log likelihood. Okay. This is likelihood. This is log likelihood. So you have this negative. So this is known as negative log likelihood. Okay. So you're maximizing, you take this and it becomes maximum. Okay. So now the minimizing KL divergence between two distributions is same as maximizing the likelihood. Now this is what is known as MLE. Okay. Maximum likelihood estimators. Now that is what we shall be looking at actually. Okay. Now famously this is known as maximum likelihood estimation. Okay. But this is same as the minimal KL divergence estimator. Okay. So now, yes, so we have just looked at it. Okay. So now how to choose the ML estimation? Now we choose P theta. We solve this optimization problem. So we always assume that now it is of, do you hear any background noise from my end? Any drilling kind of sound?
No, sir.
No, sir, no, sir.
It's fine,
It
right?
is not significant. Yes, it is not significant.
It's
good.
not. Okay, fine, thank you. So we assume a parametric form for, we assume a canonical function for the parameter, and then we go ahead. Now this gave rise to different models that we see in practice. Okay. So now, yeah, that's what finally we took a regression problem and then we use that data is from a Gaussian distribution and then we assume that the mean is h theta of x. This is the canonical function that we have assumed, and then we have assumed that the covariance matrix is identity. So that will lead us to the least square estimate. So whenever we look at least square estimate, now what is that? The least square estimate is nothing but reducing the KL divergence when we are assuming the data is from a Gaussian distribution where mean is considered to be a canonical function, and then the standard covariance matrix is considered as identity. That is what least square solution is. Okay. Now, normally what happens in whenever people look at the least square solution, now what do they have? Now they go ahead with x and y. So you have the linear model. Now that is, you have this considering that W transpose x. Okay, you consider the W transpose x or any model. Okay, no need even to restrict it to be linear. So you somehow come up with the functional way of obtaining that y. You call it as y hat, and then you reduce the square. Okay, you go ahead with MSE error and then do it, which is similar to what we see in this method. Okay, now these are two different ways of looking at the same problem. Okay, now what happens in the way in which you took y hat and other things, now things feel a lot of diversified. You don't see it as an uniformed perspective. Now our aim is here to provide a uniform perspective, now wherein which what we thought as different things combined together, and then you can see them as one entity. Okay, now this is the MLE estimate. This is how we look at MLE estimate. And then we come into what is known as a risk minimization framework. So now wherein which you have that hypothesis function, which is mapping from x to y. So and then, so this is the square error hypothesis function. Now we will be predominantly looking into 0-1 loss function. Okay, and what is the risk? Now risk is defined as the loss. Okay, the loss incurred. Now how is this functionally? This is the loss is h of x cross y to r plus. So you take the expectation of this. Okay, now what function you want? You want a function in such a way that the expected loss, which we are calling it as risk, should be minimized. Okay, so you are taking, this is known as the risk minimization framework. Now, this is what you are calling it as the risk, and then you are minimizing the risk. You want such a hypothesis function which minimizes the risk. Okay, so but what happens is we don't know this joint distribution Pxy. So what is the surrogate? Now we know by weak law of large numbers. Okay, now we can always estimate the expectation like this. Okay, and that boils down to, now this is your empirical risk. This is not true risk. Now true risk has expectation. Now empirical risk is like this because of law of large numbers. So now we are looking at a surrogate hypothesis function, so which minimizes the empirical risk. Okay, now this is what is known as empirical risk minimization, ERMs. Okay, now this framework is risk minimization because you are considering true risk here, because you are considering the expectation. Now here you are looking at the surrogate risk, which is known as empirical risk, and minimizing this is known as the empirical risk minimization. Now whatever we do, we are doing empirical risk minimization. Okay, so and then we looked at empirical risk minimization for a regression framework. Okay, and then we saw that now ERM MLE is actually same, is solving the same problem. Okay, so yeah, and then we saw that how their ERM is equivalent to divergence minimization. So what we first saw, divergence minimization is same as maximum likelihood estimation. Now we are saying that ERM is same as divergence minimization. Okay, so and then we obtained the Bayes classifier, and then we even showed that the Bayes classifier is the optimal classifier. I will not go into the details of that. Okay, So now you cannot have a classifier which is better than the base classifier. This is what we have looked at till now. Okay. So now I will first take out couple of questions that are there in the form that has been shared with all of you, and then I'll come to any questions if you have. So couple of questions that are there. What's the what's the difference between PMF and PDF? Okay. See, if you are having a discrete random variable, see, for any random variable, you will have cumulative distribution function. So only for discrete random variable, you will have the mass function, that is PMF. For the continuous random variable, you will have the density function, which is PDF. Okay. So I have taken 4 courses. See, whatever queries you have, surely let me know. So I'll surely, I have taken 4 courses for 11 credits. So whatever queries you have, you please let me know. I'll look into it. Okay. So and then there was one query on assignment 3 question 2, wherein which what is now I'll come to all your questions. First, let me finish off what is there in the form. Then I'll come to the questions. Okay, assignment 3 question 2. The model Q is encoded data. It is generated from P. What is the average code length? Now this is pertaining to the information retrieval that was discussed in length during the early classes of week 3. Now assignment 3 question 8. In the model of previous question, now that is the question that is 7th question, I think. If sigma square is increased, don't know how can you fix it. I did not get the question. So if this person is there, can you please let me know? In the model of the previous question, if sigma square is increased while kept fixed, not learnt. Now if something is fixed, now how can you increase it? Okay, then MLE objective effectively. Notes of the sessions have already been given with all the things. So p theta of y given x, now wherein which theta of x. Now y is the mean function of is of x here. That's what you take. Okay. Now, as I told you, that's what you assume the canonical form, no? Okay. So this is what is hypothesis function. That's how you assume. Okay. Better than this. Explain with this maybe better. Here. Now your output should be a function of your input, right? If you consider it as input-output paradigm, so your h theta has to be a function of x. Okay. So then images, text, sound is represented as vector in sample. It is not, no, it is represented as a vector in some d-dimensional space. No, it's not in sample space. How can we decide the random variable for this? See, we assume that the data is most of the times is from a continuous distribution. Okay, that's our assumption. Okay, for example, let's take a sample X-ray image. Now, how do you know that random variable will be discrete? See, we are assuming that the labels preferably are discrete, and then the images are from a continuous random variable. Now, that's what will be the. It's easier to see. No, X-rays assuming it as discrete random variable is not a good idea. But yeah, I answered that question. So there is a confusion that whether cumulative distribution function, probability mass function, or probability density function is used in the lecture. How to come from which one is being used? See, whenever we write, see, think of it like this. Whenever you use this P, okay, this P, no, this is distribution. Okay. On the other hand, whenever this is used, this is mass or density. Okay, that is the underlying idea. Okay, now you can see it. Most of the cases in which we are pretty much clear. See, this is the distribution. See, this is your y given x. This is prior, but yeah, this is the mass in this case because y is discrete, so it is mass. Okay. So it will be clear from in the context it is being used. Now it has to be clear. Okay. So now I'll take the questions that are there in the chat. What do you mean by canonical form? Some functional form, that's all. Okay. Increase in sigma squared while keeping it fixed is a question assignment. I'll look at it. Okay. I'm confused about the term surprisal associated. See, the idea is very simple. See, for example, if I'll take the same example that sir gave in the class. If someone says tomorrow sun is going to be rising from east, is there any information that is there? No, right? Okay. So now something that is, so it is a for sure event. So whenever you consider events which are for sure, there is no much information in it. You need lesser number of bits to take care of them. Okay. But whenever you have, so what do you call? So whenever you have a surprise event, no, at that time, no, it will be having more bits. Yeah, see, whatever is there in the notes, please consider that. There was a, while looking at the, if you look at the full video, so there was a bit of a, so plus minus mismatch that actually happened, which was rectified later. Okay. Now, whatever image that you are showing is correct actually. Okay, in the notes it is correct. While doing lecture also, at the next part of the lecture, sir will actually rectify that. Okay, there was one plus minus interchange that has happened. So while writing it is something, and finally when you look at the note is something else. So it is because of the issue. So last step in the Bayes classifier.
Sorry to interrupt, sir.
Yeah.
Regarding that entropy or the surprisal associated, right? So you mean to say that if the probability of an event is 1, then there is no information. Basically,
it's a
some
for
sort of
sure event. Yeah.
duplicate.
It will be very less information. Yeah.
But if it is 0, let's say sun will rise in west, east, in west, let's say tomorrow, then this is really surprising to us. And so surprisal is related to the information content.
Correct.
So that is related to the divergence metric that we are defining.
Correct.
Got it. Okay. Thank you, sir.
Yeah. So now the last step. So who is that? Dibya Jyoti. So is
yes, sir.
Till this point, is it clear?
Yeah, yes, sir.
Till this point, it is clear, right? Okay. So now here, now it is belongs to S1. Okay. But now actually the data is from 0. So see, when do you, okay, intuitively think of it like this. Now you have, now for any given input, either this integral will be evaluated or this integral will be evaluated, correct? Is that clear?
Yes, sir.
Okay. So now which integral will be evaluated in between them? So the one, if you are saying it as 0, it might belong to 1. So the other integral, now whichever is the minimum one will be integrated, right? Now depending on your class conditional, okay, or the posterior, whichever you consider, okay, y is equal to 0 given x. For an example, y is equal to 1 given x. These are the two things. So for what you will classify, for whichever one there is the maximum value or the highest value. Now if you say that it is 0, now the minimum one, now when do you say that it is 0? This has the maximum value. So therefore the risk will be evaluated with respect to this.
Yes,
okay.
sir.
That is why we use, where is this min here? Okay. Is that clear?
So that means at every point we compare both the probabilities, both the product terms, and which one of them is the smallest, we take one. That one.
See, for whatever is your input, you will get the so for whatever x that you will get two things. Probability y is equal to 0 given x.
Yes, sir.
Probability y
The
is
class
equal to 1
probabilities.
given x. Correct? Is this
Yes,
clear?
sir. Yes.
So now consider that this is bigger. Is that clear?
Yes, sir.
So let's say that this is 0.58, this is 0.42. Now then, with respect to this integral will not be evaluated. With respect to this, the integral will be evaluated.
Yes, sir.
Got it?
Yes, sir.
That's all.
Thank you, sir.
So sir could explain. So in the screenshot, second line, consider first line. Yes. So can you explain some mathematical example for each topic? No, we are doing it, right? Most of the tutorials is exactly that. Okay. Yes, Utsav, please go ahead. What is your question?
I have a curious question, sir. That
Mhm.
we saw that initially we make an assumption that about the probability distribution that our data comes from so and so probability distribution. For
No, it
example,
is.
in this case, we
See,
made
it is not an assumption. It has to come, right? We don't know the distribution. We make a assumption for the distributional form.
no,
No.
I'm not talking about this. In the examples, in the example where we talk it, that for MSc, that our data set comes from Gaussian distribution,
Yes, yes.
and the mean of that is
Hmm.
h of s theta.
Hmm.
So the question which came to my mind that in this case we are assuming it to be a Gaussian, but
Hmm.
we would have assumed it to be exponential or Poisson or any
Yes, yes,
other.
yes. You can.
So in real world, what is the correct which assumption should we make it? We don't know.
See, here, if you assume that it is a from exponential distribution, that will lead to one model. If I assume that it is from Gaussian distribution, that will lead to another model. All models are wrong. Some models are useful. Okay. We
So it
don't
is
know.
like
We are
that.
dealing in, see, we are dealing in dimensions that we don't know, Nupa. Okay. No, always remember this. This is the, what do you call? We can only say that all models are
Wrong, but
wrong.
some are
Only some
useful.
models are useful. Okay. Now, why do you take Gaussian distribution? No, because there is log inside, there is log outside, and then there is exponential inside, so they nicely cancel off. So you get nice forms. Okay.
Okay.
So map estimate non-parametric, that is week 5. It will come.
So that was I was thinking that it is not like a loop that I'm taking an assumption, I'm coming to the risk minimization, I'm thinking it is not a good function, then I'm again changing the assumptions. That is what I was
So
thinking.
most of your questions will be answered when we go to neural networks. Neural network is universal function approximator. Now you put
Oh,
in things will work. Wait for till that time. Okay, it's a
okay.
very valid question. All of you should have that question. Now, what is this? We get so many things actually. Even if you assume exponential, you get something else. You may not get this form actually. You get, now what do you call? You get with norm. You get with what do you call, MEIE. Okay, you get that absolute function. Okay, I'm not able to get the word. So whenever you make an exponential assumption, that's when you get MEIE laws. Okay, so yeah. Now again, why are you taking exponential? No, because log is there, exponential is there. It's easy to handle. No, why can't you take any other distribution? So yeah, it will be difficult to handle actually. It's a computational convenience that we are dealing with. Yeah. Yes, Ayed? I think there is a very nice noise from your end. You're traveling, I guess. You can type the question. You please type the question. Yes, Taran, go ahead.
Sir, in base classifier, sir
Hmm.
says that our function that we are going to choose is it will be 0 if probability of y equal to 0 given x is greater than probability of y equal to 1 given x. But how do we calculate that probability? Will that come next or?
Yes.
Hmm.
That will come next. So finally, how do you calculate this? So what do we do is we assume, not assume, we actually split them into prior and then class conditional. Now prior can be calculated because of the data. Okay, if your data has 2 classes, now let's say that there are 100 examples. In 100 examples, there are 75 examples for one class and 25 examples for another class. And then it is 3 over 4 is this prior and 1 over 4 is this prior. So from data, we can obtain the priors. And then we assume specific density for the class conditional. think we have done this. Maybe it comes in 4th week tutorial. You have a full-fledged, what do you call a section in which we actually estimate the parameters and then we obtain how do you get the discriminator function and stuff and other stuff. Yeah.
Sir, a confirmation on this, on the proof of this Bayes classifier.
Hmm.
Risk associated with the hypothesis function RH, it is integrated over S1 and S0.
Hmm.
Yeah. So, but in RHB, we have mentioned it is in R to the power D in D dimension, right?
Hmm.
So can we assume here RD equal to S1 plus S0 or
So you
S1
cannot
union
say union of that.
of that? Yeah.
Yeah, it's actually correct. So you have to, that's how we have, you can see it here only, right?
Okay.
Okay.
Right.
So there is no intersection point between your regions of 0 and 1. And when you consider the union of them, you get the whole D space.
Yeah.
D-dimensional.
And intuitively, I can also write RH equal to integral of, let's say, the first term. I am integrating over the domain S1. I can also write it like domain R to the power D. Others will be automatically it gets 0 whenever it falls into the
See,
S2 domain.
See, for example, what is SI? Now, when your hypothesis function is saying that it is I. See, if you look at this, see,
In case of 0,
S1,
1,
whenever it is S1, you are considering the class conditional with respect to 0. Why? That is what the risk is, right?
Right. I mean, for sake of mathematical interpretation in an easier way, I can also write this integral domain to be, I mean, S1 plus S2 in the first term and in the second term also, and hence R to the power D. So it is addition of two positive numbers in R to the power D.
See, you do one
versus-
thing. Okay, you do one. Just write it down on a piece of paper and put a image in our discussion forum. I'll answer there.
Okay,
Because
sure.
I'm not able to
Follow. Yeah.
follow that. You just put it in writing. That is much more clear. Even for you, most of the times when you write, things will be clear.
Sure, sir. Yeah. Sorry for that. Thank
Yeah.
you.
I asked the question regarding the confusion in distribution function, mass function, density function. Can you read the full question and then answer it? You answered the first part only. Okay. Sometimes the notation used is P of X is equal to X, but the terminology uses distribution function to refer it. So shouldn't it be? Yeah. So no, I don't know which instance you are saying. If it is there, don't worry about it. Okay. You just consider it as the density function and go ahead. Okay.
Sir,
Yeah, please go ahead.
sir, in the week 3, towards the end part of the videos, sir talked about the concept of generalization bound that people used to give before the advent of neural networks. So, sir told that the generalization bound used to be defined as an upper bound on the true risk. So, could you explain on that? Because
See, don't go in that direction. No, that is so it is something that is what do you call null and void
Okay.
in the current day situation. If you really want to understand properly the bounds, please go and look at in NPTEL itself. There was the earlier version of this course called as pattern recognition neural network. Now, if you see that, okay, that is by Professor Shastri. Okay. So if you look at those videos, there he has entire set of videos on bounds, VC dimensions and other things. You can look at it there. Now, actually, in institute, the course is still called as PRNN. That is the reason why you still see all my notes name as PRNN. Okay. Yeah. So that's a legacy course. So you can look at it.
Sir, actually, I tried to read about it and I found out that the entire concept of generalization bound, it does not even fit for neural networks,
you
because
cannot actually.
the
Correct.
same theory says that neural networks should definitely overfit and they should definitely,
Correct.
perform very bad on new data. But we know empirically that neural networks perform very well and generalize very well. So there is no theory explaining.
Wait. Your question will be answered when we go to overfitting. Don't worry.
Okay.
Keep that question. Okay. So whenever we
And-
say whenever we say distribution function, we always mean cumulative distribution function. There is distribution function is cumulative distribution function. Yeah, please. Someone was saying something. Yeah. Yeah, please go ahead, Taran. Please.
Sir, so in many of the lectures, sir has said that we are finally estimating a distribution, and it depends on type of problem that we are
See,
solving.
you want
For
to
example,
estimate distribution, and then you will estimate densities finally.
yeah.
Hmm.
For example, in a regression problem, we will try to estimate a distribution that is of form a probability of y given x.
You will estimate
And
density per again.
yeah, and for sir, so basically, sir said that for GPTs, they try to estimate the marginal of x. Can you explain that? And for classification problems, what density or distribution are we estimating?
See, now for GPT, and what is that they're trying to achieve is P of y given x. This is what they're going to finally tell, which is actually known as the posterior. This is estimating finally this. This is exactly what you will be having now when you have even for classification. Now, if your x is an image, now then what class it belongs to? Now, if it is GPT, now then what is the given the input, what is the next word that is being predicted? Okay. Now the way in which you look at the problem is what that modifies. No, but always you will be estimating P of y given. Most of the cases will be at least in this course, unless specified, you will be always estimating the posterior y given x. Now P of y given x. So we will split them into P of y into P of x given y. This is class condition. This is prior. So and then we assume a form for class condition and then proceed.
And sir, P of x given y is easier to compute. That's why we divided it in that form.
No, see, may not see. I don't want to say that it is because of that. We use that. That's all. I don't know what is easy, what is difficult. It depends on question to question, no, problem to problem. It depends. Okay.
And sir, what type of questions would have us estimate marginals?
See, now consider the case in which you want to sample from PX. You wait. That is what is there in 4th week. Okay. You will get your questions answered in 4th week. Okay. For sampling from P of X, so you should understand the distribution of PX. So then you go ahead.
Sir,
Huh.
Sir, all the types of generative models that are currently available in the market, be it, conditional text generators or conditional image generators or video generators, in all of them, can we say that we are basically estimating P of y given x, that form?
Yes.
We are not. Sir, can you give me an example of a case where we estimate marginals specifically?
That's what I told you, right? If you just are, see, so this is y given x is your conditional generation. If it is just px, then it is marginal, no?
Yeah. But sir, do we
Sometimes you
generally?
even generate x given y, label given the input. See, it depends from task to task. See, now as you go along, that is why we write it as v. We don't want to bring in any of this x given y, y given x, p of x, p of y. No, these everything can be considered as this v.
Yeah.
Depends from problem to problem. See, that is the reason why we don't want to bring in any of these notions. So the overall idea is you are estimating distributions, okay, or densities, whatever.
Okay.
So that is the reason, irrespective of the problems may vary, because of which the density that you are estimating may vary. Okay, no, it all depends on semantics. Now that's what the aim of the first class, right? To say that no, come out of the semantics. Think of it as a data coming from a distribution.
Sir, I have another question. So while discussing the KL divergence metric for comparing two different distributions, the one that is the original true distribution and the one that we have assumed on the basis of the data, sir told us that the KL divergence cannot be called a particular metric because it does not satisfy the
Triangular law
property. Then, sir, why are we going forward with KL divergence? why should not we go forward with someone which actually satisfies the distance
So
metric,
very
like
good question.
Jensen-Shannon divergence or any other one?
Very good question. Okay. Now, the reason is KL gives us nice forms. That's all. Easy for us to compute.
So is that the only reason? Like, do you have a justification?
That's all, pa. See, what do you want? You want something that you can mulch, no?
Yeah. Okay, just so we can express the terms in a quantifiable manner and we can have something to work upon. That's why we choose the
Correct. See,
KL
that is the
divergence.
reason. See, no, these kinds of questions needs to be asked. Now, that is the reason we are teaching it this way. Now, if you come from a standard deterministic way of teaching things, I'll start with regression. You will not even understand it as divergence minimization, in which
Yeah.
now we are very happy to say that KL is the only thing we use. There are a lot of things you go and explore. Now, those kinds of generalizability is the aim of this course actually. And
Okay.
give you that generalizability and then say that, see, this is working, so you are using this. So that if you have an option of using something else, you should be go back to the basic ideas, to the scratch, and then do things up.
Okay. And sir, do we need to study any part of like measure theory for this course?
No, pa, no, pa.
Oh, okay.
See,
And for
initi-
estimation theory?
no,
Uh,
estimation theory is also not needed. See, now whatever you need here and there, some, what do you call, brushing here and there is needed. Apart from that, don't go deep into any estimation theory or anything, any measure theoretic idea of things. We don't need it. See, we will not be even uttering Borel sigma algebra from now on. Don't worry. It was needed only at that point to make a point. That's all. Somehow to appreciate you that finally everything is a random variable. To appreciate
Okay.
that point, we wanted Borel sigma algebra to be kept in place. Now, apart from that, we will not be even uttering that word from now on, unless you ask us.
Okay. Thank you.
Yes, Utsav, go ahead.
I don't have a question. I just have a bit concern
Hmm.
that we are studying everything from scratch, and it is very good for the research perspective, and we to implement so that we can build our own ideas.
Hmm.
But sir, in research, we also have to code our experiments.
Correct.
So,
You will do
sir,
it.
can we not? So can you shared a PDF for the probability theory?
Yes.
So can you please share us with some notes or something to see the coding parts also?
We
the
will only
coding
do it
parts?
in tutorials. Don't worry.
Because I'm thinking maths is becoming easy to me, but coding is becoming little
Good.
more.
Very good. You're in right direction. See, coding, no, GPT also can do it. Pa. Why do you worry about coding? Nowadays, you have that vibe coding, no?
Yeah, but sir, while converting our ideas into experiment, it requires our intervention.
Yes. See, coding we will do. Once we go into the week 5, now we will have a lot of coding experiments. Don't worry. And
Okay.
as we go along through the course, you'll have more coding. So coding will increases as you go along in the week. That is the reason why we had a separate tutorial video on giving the basics of Python. You will have
Okay.
coding, don't worry. So can you suggest any NPTEL or any other course for referring basics of probability theory? See, in my view, there are nice courses on probability theory. For example, one is by Professor Krishna Jagannathan, but it is fully measure theoretic. Okay. So you can take the book Sheldon Ross and then review it, or I have uploaded that probability material. No, go through it. That is more than enough. That is more than enough, actually.
Sir, in the first week or probably in the first week, Prathosh sir actually told us while discussing, the concept of a label, that the entire concept of a label is a human-made construct.
Correct.
So if sir told us that he would in the later part of the course, he would give us an assignment where we will have to randomly label images. So sir, I did that, and surprisingly, I found that the universal approximation theorem holds even if you randomly map MNIST digits
Correct. That was the overall idea, right?
Exactly. You get the same accuracy, like 98%
You'll
exactly
get
same.
it. You say anything. See, leave that pie. You take a small kid and teach 1 as 2, 2 as 1.
Yeah.
Got problem solved.
But sir, that also signifies that these models do not exactly understand what 0 means or what 1 means. They just find a mapping between these two.
See, there is nothing to understand. It's a human construct, no? What is there to understand?
It's like we are teaching a kid to identify 0 as 1 and then 2 as 3.
Ah,
So he will naturally believe us and will start
correct.
studying like that.
Correct. That's what you have
Yeah.
done. That's what you have done actually. So you should. So these are interesting questions. So have you seen this quantum mechanics nice video? This okay. I'll just
Which
show
one,
you
sir?
one. I'll just show you one video. Wait.
Are you talking about a professor giving introduction of quantum mechanics that I
Ah.
will make you understand that we understand
No.
nothing?
Wait. Don't tell that. You should. Able to see this?
Yes, sir. I have seen this one
Very
many
exciting.
times.
That's fine. Is the audio there?
Yes, sir.
They start quantum mechanics, and that's how we do to the end of the term. Now, I got bad news and good news. Bad news is that it's a subject that's kind of hard to follow intuitively. And the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense, the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I'm the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else.
All of you are asking right questions. It is exactly like this. Now, why a neural network work? None of us knows. It's working. It is working. That's all. That random labeling is shocking. Actually, it's shocking. Why it is working? But anyhow, it's working. It's working.
Sir,
Have you guys read a book called as Nexus?
no.
Read a book. So first you should read Sapiens before reading Nexus. Then read. So take that and then read it. So yeah, you'll understand Nexus. Before that, read Sapiens, Yuval Noah Harari's book. So how about 4-week probability taught by Will It Survive? Yeah. 4-week is enough. So actually, no, we are planning to have a course on probability. But anyhow, when it will, what do you call? No, we understood that people actually need a nice course on probability after starting machine learning course. Okay, so we will be doing it actually.
Actually, sir, in reality, in many of the colleges, the courses that we are given regarding probability, they generally completely ignore the part on the sigma algebra. I only heard it for the first time. That's why I was asking you.
Any courses in probability start with coin tossing, end with coin tossing.
Yes, sir.
And you don't need coin tossing at all anywhere.
Yeah.
So don't worry. So we are planning to have a nice course, but yeah, for the future. So we also understood that problem. But late. Yeah, but anyhow, so yes. Next, who is this? Shanmuga, please.
Yeah. Hi. Actually, I just finished a 2 weeks video. I in the last second video, end of the second video, sir mentioned optimization problem, estimating the parameter data. I did not get the complete picture of this formula. Theta star equal to argmin of theta d into px p theta. My understanding is we can find parameters from the data input data, or it is a parallel thing,
See,
px and p theta.
think of it like this. Okay, we'll give a better idea of this. See, for different parameter, you will get different loss. Can you appreciate that point?
Definitely.
If you change the parameter, you will get a different loss. Now, what parameter you want? You want such parameter in which the loss is least, correct?
Yes.
That is what argmin is referring to. Got it?
Okay.
You want such
and
parameters,
yeah.
because of which the divergence between the true distribution and then the actual distribution, the true distribution and then the assumed distribution reduces.
And sir also mentioned we have a billion type of parameters.
We not billion types of parameters. We have billions of parameters. In GPT, we have what we know is 1.7 trillion parameters. But yeah, go ahead. How do you solve it will be your next question.
Yeah, is it a parameter or a data? Because I assume it is a
It's
data.
parameter. No, it's parameter. No,
Then
don't
the
worry.
combination, yeah.
No,
Then the
no.
combination of data and the multiple parameter will multiply.
See, data is what you give as input. Parameter is what that is based on the, for a given input, it will compute an output. Okay, that is what parameter is. Now, for example, you have y is equal to wx plus c or mx plus b. X is your input, mx plus b, m and b are your parameters. What is the output is your thing. That is a line actually. Okay. Now you can consider it as a simple line there till GPT for that matter.
Thank you.
So does that mean we can build a random model? Yes, for sure you can actually. We have tried it. It works. But
Sir-
all the semantics should be similar. Yeah.
So till now, what we have done, can you just connect it back to a random experiment? I mean, how does that look? For example, we are looking at a
See, now connecting back to the random, see what is that you're trying to do? Finally, you're trying to obtain a function, correct? Mapping from x to y. That's what you want?
Yeah.
Now, how do you do it is what you're discussing. All your things. Now, how is your MLE and this is connected? Divergence minimization is connected. How is your risk ERM and then your divergence minimization is connected? So if you think of it like this, now it is the same thing that we are trying to assume. We are trying to label them or whatever. You're trying to find a distribution or density, which are equivalent. And equivalent in the sense in obtaining the results, not their equivalent in terms of operation. Okay, that's what you're trying to do actually. You're finally trying to assume, so no, you're finally trying to estimate either P of X given Y or P of, depending on the data, you're trying to estimate a distribution. That's what you're trying to do, which is exactly similar to now whatever we have started. X-ray is from Px and then label is Py. So and then you have a joint distribution Pxy. Finally, you want to say that what is the probability for a given X? You want P of Y given X is what you want to estimate. Now, how do you estimate P of Y given X? There are so many ways. Now, which is the first way? The first way is MLE, which is maximum likelihood estimation. That is nothing but minimizing the KL divergence is the first one that we have taught. And then the next one that we looked at is risk minimization framework, which is equivalent. Okay. Does it connect the dots?
Yeah.
Sir,
Hmm.
Sir, in the last video of week 2, sir, week 3, sir took the example of the Bayes classifier to actually show us how the empirical risk minimization framework works out and to establish an equivalence with the probability distribution estimation that we did. But sir, in the process of estimation, empirical risk
See,
minimization.
now you assumed that the least risk can be obtained only with Bayes classifier. Is that clear?
Yeah. So that is
so now
clear.
what is that your final aim is to get a Bayes classifier now?
Yeah.
Now to get the Bayes classifier, what do you need? Now you need class conditionals and marginals, correct?
Yeah.
That's what you're estimating.
Sir, I am saying is that during the starting part of the proof, we have assumed that the data, we have assumed a Gaussian distribution in the first part. So
No,
can
no,
we
no, no,
proceed?
no. While going with that proof, we did not assume it. While going ahead with that proof, it can be from any distribution. And even for that matter, there is no need for distribution also.
Yeah, I'm
Just
asking,
from
can
RD.
we go forward without, taking any distribution for granted, and we let the data find out the
That's what we
parameters?
have done there, no?
Uh,
Exactly. Let me show you. Just turned it off. That's what you have assumed, right? You haven't taken anything here. So you have just considered the risk and then you have went with it. That's all.
yeah, got it, sir.
Got it?
So the tutorial videos that you have taken and those are uploaded, sir, will those notes be available?
Is it not given already?
No, sir, we are only given the notes of Prathosh, sir, the lecture
Okay.
notes.
Don't worry, I'll give it. Don't worry.
Oh, thank you, sir.
Yeah, again, I don't know whether you know it or not. Tutorials are optionals. We are just exploring on couple of proofs and then there is no philosophy discussed there. In the sense, philosophy of ML, not philosophy of philosophy. Okay. Now, there is no, what do you call, philosophy discussed there. It is just couple of numerical examples and then couple of, what do you call, proofs that were left during the sessions. We'll be filling it up in the tutorials and coding as we go along. That's what tutorial is meant for, but your contents is from the main thing. So I'm asking about the link where download NPTEL notes. See, it should be there in the portal. Please go ahead and look at it. Okay. So any other questions? Okay. So, Sir Sapiens, the other book is Nexus. Yeah. So we will have everyday live sessions. Please attend. So yes, Shatru,
Sudarshan. Yeah.
Sutarshan, yeah.
Yeah. Sorry. I might jump ahead. Sorry for asking this. I just looked at the videos which has been uploaded in the YouTube. I think it's for the week 4. And the problem is whenever Mr. Prathosh explains the optimization problem, I just noticed that he leaves out the expectation which should be in front. I mean, just the average. Is there a specific reason he does that? Because it changed the entire meaning. No, it's like.
Can you tell me which part he has done that?
Okay. Just a second. Well, it's not uploaded in the course yet, but under the.
Yeah. Okay. Even there, which part?
Okay. Let me see. Just give me a second.
Yeah. Sure.
Okay. For example, lecture 21.
Which part he's saying?
In lecture 21, well, he starts to motivate that we have to reduce the difference between L theta and the other one. I'm sorry. The beginning of lecture 21. Yeah.
This one.
Let's go here. Yeah, this one. Yeah, let's go to here. So the actual optimization problem would be having there would be an.
Can you see this? What I'm circling?
Okay.
Got it?
Okay. Probably this was not mentioned in the. This was not shown in the.
He has verbally said it. I just made a note of it. That's all.
Right.
Okay. So for this specific case, we are only considering one data point. That is the reason why he has left the outer, and he will be repeating it multiple times. There is again one more summation outside where in which it is going from I to n. I is equal to 1 to n.
Okay. Okay. And just one final question.
Go ahead.
In the algorithm he explains for En, uh,
Hmm.
the steps. Yeah, the second one.
Hmm.
I have trouble understanding the second step because
This one.
already well, the second step. I'm more confused about the second
No,
step.
no. Which side? You're saying about
Oh, so
maximization step.
yeah, the maximization step.
Hmm.
So already like okay, correct my understanding if I'm wrong. Maybe I could have understood it incorrectly. We start with the initial guess of theta. I mean
Correct.
parameters, right? And that's how we arrive at f theta of q. So already the f theta of q has been estimated with like with the initial like a guess of the parameters. So how when you say that okay, theta t plus 1 should be the argmax of the f of theta, then I struggle to understand like how can you like already theta is mentioned for that problem, right?
See,
I'm just
now please remember this.
okay.
This and this can be
Mhm.
estimated at different thetas.
Sure.
Correct?
Mhm.
That is the answer for your question. This
Okay.
and this can be estimated at different thetas.
Yep.
Okay, now let me tell you what is happening.
Okay.
See here, what is the theta that you are considering in this case?
It's an initial guess, right? Like
The theta t, whatever, at the t
yeah.
step.
Yeah, okay.
Okay.
Mhm.
At this point, what is the theta that is there? This. It is again theta t.
That's the same. Yeah.
Now, at this point, what is the theta?
Again, it's the same theta t.
Theta t.
Yeah.
Now, in this whole thing, it is theta t.
Yep.
Theta t plus 1 is coming here.
Yep.
And then you take that theta t plus 1
Mhm.
and then put that theta t plus 1 here and get this next.
Okay.
See, I got your question.
Mhm.
Okay. So in the next week,
Mhm.
how did this should not have come, right? How did this come?
Well, I seem to be
Okay.
following.
But anyhow, okay, YouTube is
okay.
fine. Okay, in
Okay.
week 5, we will have a specific tutorial in which this whole thing will be actually coded, and then we'll take an example. At that time, it will be clear. Don't worry.
Okay.
Okay, in week 5, it will come. We are
Yeah,
preparing
thank
the
you.
notes. It will come there. Now, again, in week 5 beginning, he explicitly, this question was asked even in the class, post class. Now, he answers that. And here is the answer for your question. He represents it at a different notation, and then he explains this. Again, he explains this. Don't worry.
Okay.
Once the week 5 is released, your query will be answered.
My apologies. I just jumped.
It's fine, no problem.
Okay, just like one question, just out of this context. If I have doubts, just any conceptual doubts, apart from me asking to you here, is there any helpline or like maybe an email which I could possibly, or a forum maybe where I could?
See, there is that Google discussion forum is there, no? There is one Google discussion forum.
I don't see it anywhere. Probably I can ask someone.
There is
from the
one
chat maybe.
Google discussion forum that is there. Now, there also
Okay.
you can post your questions. Now, there, now again, either I'll be answering or students are also allowed to answer. No, it's a discussion forum. There also you can put the things.
Okay.
Okay.
Well, that's it. Thank you so much. Yeah.
Yeah.
Bye.
Where to find the tutorial class timing details? Tutorial class are also recorded. Okay, and then it will be uploaded. So it's not like any. It will not be like any live session. Okay, tutorial class is recorded again. It will be recorded in my lab. It will be recorded in my home, depending on where I am. It will be recorded and then put. That's all. Yeah. Okay, pa. We will conclude today's discussion. Thank you all for patiently listening. So I hope you are all enjoying the course. So any questions, please put it in the discussion forum. Every day, apart from weekends, I'll be looking at and then answering your questions then and there.
So one final request, could you please upload your personal notes like you used to on your GitHub? There is only till
Yeah. See, what happened was lecture 8, I was absent.
Oh.
I haven't written that notes. That is the reason week 4 has not yet come. I'll write it and
No problem, sir.
Yeah.
Once you write
tomorrow
it, could you please upload
Sure,
them?
sure.
Thank you, sir.
Okay. So thank you all. Whatever queries you have, you can put it in the discussion forum or do it in live sessions every week that is there. Okay. Thank you all. We'll meet next week. Bye-bye.